Okay, so basically we have discuss up until the FP, right? Okay, so after your mid-semester break, I'm going to discuss about Fletcher Reef, which was scheduled on Monday. So I'm going to give you the recording video on this FR method. So this FR method is quite identical to Steeples and Newton, but different search. I have explained earlier. The difference is on what? Steeples descent, use Hessian matrix, Newton use inverse Hessian, and Fletcher use conjugate gradient direction method. Okay, Steeples descent use gradient. Sorry, Newton-Raphson use Hessian matrix. DFP use inverse Hessian. Okay, and then now conjugate gradient use another coefficient of conjugate direction. So basically, the methods are quite identical, but the difference is on how it accelerates towards the solution point. So I'm going to give you the recording video on this method. So as for today, we are going to discuss about the constraint. Okay, there are methods of constraint which are equality constraint by theory of Kant-Tucker. Then we are going to proceed with Kant-Tucker and modified Hooke and Jeffs, and also modified Hooke and Jeffs search method. Okay, and then penalty function. So actually we have left only with three methods. Okay, Kant-Tucker, modified Hooke and Jeffs, and penalty function for constraint optimization. All right. So now what we have discussed previously, okay, we have done with unconstrained. Okay, we have direct search where we have discussed Fibonacci, golden search, and then we have interpolation search for cubic, dividend, and quadratic. Okay, and then n-dimensional search for XD, Steeples descent, Hooke and Jeffs, Newton, DFP, BFGS, and then conjugate for Fletcher Reef method. So all of these are from unconstrained optimization, where the problem has no constraint. Okay, now we are going to discuss about constraint optimization, but the solution is quite identical with unconstrained, but before that we need to deduce to unconstrained. Okay, so for constraint optimization, the very first method is to deduce to unconstrained, and then we can find the solution. Okay, you know how to find the solution of unconstrained, but now for constraint, the main point is to deduce it to unconstrained, then you can find the solution. So there are two types of constraint optimization, which comes from equality constraint and inequality constraint. Okay, if the constraints are in terms of equality constraint, then we can use Lagrange. We have discussed Lagrange earlier, but don't worry, we're going to discuss again today. And then for inequality constraint, where it has greater than, less than, greater or equal, less than equal, we are going to use Kant-Tucker. So all of this method is used to deduce to unconstrained, and then we can find the solution for this constraint optimization. All right, is that clear? Okay. So now, what is constraint? Okay. So actually, I'm going to share these notes after this in your e-learning. So let's just use this note, okay? Because I have the notes with Malay in language. Okay, there is no notes in English language, so I'm going to translate the notes here, so you can refer to this note after this. Okay. Okay, now what is constraint? So let's discuss about the general form of constraint here. So in the previous unit, we have discussed about unconstrained. They either had no boundaries or the boundaries were soft. So there is no boundaries, we just find the solution point. Let's say we use what? We use direct search. So we have identified the interval along the solution process. Okay, now in this constraint optimization, we will be examining situation that involve constraints. So there are constraints. So here are constraints. So we are going to find the extremizer within the constraint only. So a constraint is a hard limit placed on the value of a variable which prevents us from going forever in certain direction. Okay, so the area of finding the solution is limited to the constraint. Okay, so with a non-linear function, the optimum values can either occur at the boundaries or between them. So maybe this is your maximum point, maybe this is your minimum point. Okay, maybe this is your maximum. So this is for non-linear function. And for linear function, the optimum values always occur at the boundaries. So if it is a minimum point, then it is here. If it is a maximum point, it is here. So as you can see, this is the difference between nonlinear and linear function in finding the solution point for constraint optimization. Okay. Okay, so now let's see. So let's say we have an objective function, okay, z equals to fxy. Okay, so we have these two variable function, the objective function. Let's say, okay, we are discussing about the equality constraint first today. Okay, so let's say we have the constraint of g xy equals to 0. So this is the objective function. This is the constraint. All right, so now in order to find y, okay, we can have, here we have x and y, right? Here we have x and y. So we are going to use this constraint to find y. Let's say y equals to hx. So y is a function of x. So here, okay, but it is quite difficult to find the function of y in real situation. However, we can differentiate the function of y here, okay, means that we differentiate also h. All right, so this y comes from this g. So now it is equivalent by implicit differentiation. So this dy dx, okay, this dy dx is equivalent to the derivative of h, okay, because we want to find h, and this dy dx is come from the implicit differentiation of g, which is minus dg dx over delta g delta y. Okay, clear not up to this point? So we are going to minimize the function z here, okay, when we want to minimize the function z here. So now, as you can see, okay, z is in terms of f and y is in terms of h. So we can write z is in terms of f here. fxy now is in terms of x and hx. All right, okay. And then the sufficient condition in order for us to find the minimum point of z. So in order to minimize z, okay, so the sufficient condition is dz dx equals to 0, right? Where this dz dx is equals to, here is f, okay, df dx plus df dy times dy dx, because we have y there, okay? So it is equivalent with df dx plus this one. This is your dy dx, right? So df dy and dy dx. Okay, sorry. Okay, df dy, dg dy, dg dx. So coming from this, so we are going to have this. This one equals to 0. Okay, so solving this will give you the point of x and y, which minimize z. So this is where does the Lagrange multiplier comes from. So we have discussed Lagrange multiplier earlier. Okay, so now how can we find the general form of Lagrange that we have used previously? So now by solving this function, okay, by solving this function, we are going to have point x and y. But let's say if we substitute minus delta f delta y here with lambda, sorry, lambda here minus delta f delta y here with del over del g del y here. This one. Then we are going to have lambda here. Okay. Now substituting this, we have gxy equals to 0. Okay. And then del f del x plus lambda del g del x equals to 0. Okay. So another one is del f del x plus lambda del g del y equals to 0. So these are the starting point of where does Lagrange multiplier comes from. Okay, so we are going to solve del f here equals to 0, del f del y equals to 0, and del f del lambda equals to 0. Then we're going to find the value of x and y in order for us to minimize the objective function. We have done earlier, right? Remember? So this is the notes for Lagrange multiplier. We want to maximize or minimize the objective function such that to the constraint. Given the constraint here is equality constraint. So for this case of constraint, when it is in terms of equality constraint, we are going to solve by using Lagrange, where the Lagrange multiplier comes from this necessary condition. Start with del y, del x0 here. So substituting everything, then we can substitute this with lambda, and we are going to have this general form of this Lagrange multiplier. So how can we find the solution? All right, let's try one example. Let's say you want to minimize where the constraint is 4 minus x minus y equals to 0. Okay, so first we are going to have a function of f here, where f equals to f plus lambda gxy. So fxy lambda equals to x square plus y square plus lambda gx, 4 minus x minus y. Okay, and then from here you can find del f del x, del f del y, and also del f del lambda. And then equal them to 0, solving the value of lambda, x, and y. Okay, try. Find the value of x and y here, and also lambda. Okay, got it? Right, so solving this will give you x and y both equals to 2 and lambda equals to 4. So substituting x and y here in f will give you equals to 8, which is minimum, because we want to minimize. So minimize the function of f here. When x and y equals to 2, then the minimum function is equals to 8. So this is how we find the extremizer by using Lagrange multiplier of equality constraint. Okay, any question? What we have discussed just now is constraint optimization, and there are two types of constraint: equality and inequality. Where equality constraint, we're going to solve it by using Lagrange, where the derivation of Lagrange comes from this necessary condition. Okay, and then we are going to have this general form of Lagrange multiplier. After that, we just differentiate, equal them to 0, for which they are all sufficient condition to find the extremizer. And then find the value of x and y to minimize or maximize the objective function. Okay, clear now? Any question? Okay, try this one. Determine that point 2, 2 is a minimum point for x1 squared plus x2 squared to x1 plus x2 equals to 4. So this is the constraint. This is the objective function. Okay. You know that this is your minimum point, but determine how that this 2, 2 is a minimum point for this. Okay, try. After this, we discuss. Okay, so for this case, the objective function doesn't mention whether it is a minimum or maximum, but we want to identify that either this 2, 2, this point 2, 2 is a minimum point. So how can we find it? So of course, we know that we can solve this constraint optimization problem here by using Lagrange, where we have f(x1, x2 lambda, right? So we have here x1 squared plus x2 squared plus lambda 4 minus x1 minus x2, because you know that this g is always 0 here. Okay, so we just put this one as a 0. So this is your g. Okay, so now solving this, we are going to have del f del x1. Okay, and then del f del x2, del f del lambda. So del f del x1, here we have 2x1 minus 4, this one 2x2 minus 4, and then this one is what? Del f del lambda here is 4 minus x1 minus x2. So solving this equals to 0, all of these three equation equals to 0, we are going to have x1, x2, and lambda. Okay, so now we don't know this point is a minimum or maximum. Hence, we can find this by using what? Any idea? How can we obtain the maximum or minimum point? We can check the function of f here by using what? Yes, Hessian matrix. So this is the first derivative. So finding Hessian, just differentiate again with respect to x1 and x2. So we will have here fx1, x1, fx2, x2. Right. Okay. Where your Hessian is 2002, and check the minor principal components. If H1 here equals to 2 greater than 0, H2 here equals to 4 greater than 0, then what? All of the value of Hessian here is a positive. Then what you can conclude? Positive definite. Then what? When it is a positive definite, then hence 2, 2 is a minimum point, right? Since H is a positive definite. Okay, clear not? So this is how you solve the extremum point of constraint optimization, which is equality constraint. Okay, clear not? Any question for this part? Okay, it's quite easy, right? Because you have done this earlier. Okay, can we proceed? Is there any question before we proceed? All clear? Okay. All right, good. So now let's proceed with the next type of constraint, which is inequality constraint. Okay, so this inequality constraint, we are going to discuss about the Tucker condition. Okay, but now let's identify, let's analyze about this inequality constraint first. Okay, so now okay, now in equal constraint, we have equal sign, right? So now in this inequality, okay, the idea of Lagrange multiplier now is extended to the inequality problem, such as, let's say we want to minimize the function of x where it is subject to, previously we only have what? Previously, we only have the function and gx equals to 0. So this is for equality constraint. Okay, but in equality constraint, we are going to have that gi less or equals to 0 or greater or equals to 0, and also there are equal constraints here. Okay, where I equals to 1, 2, until u, I here equals to u plus 1 until v, and I here equals to v plus 1 until m. Okay, so this is the general form of inequality constraint, all right? And this inequality constraint can be converted to equality constraint. So in order to solve this, we are going to convert this inequality to equality, but with a certain condition, of course. Okay, so how can we convert? Okay, let's discuss about this. Okay, now this inequality constraint can be converted to can be converted to equality constraint by adding some sort of slack or surplus variable. Okay, so in order to convert this, we are going to add slack or surplus variable of x and plus 1. Okay, so how? Okay, now by adding this slack or surplus variable now, this problem can be written as subject to When it is less than, so we should plus with the plus, then equals to 0. When it is greater than, then we should just minus with slack variable, then it is equals to 0. And then this one is already equals to 0. Okay, clear now up until this. It is inequality. Okay, now we are going to convert to equality by adding the slack or surplus variable. If it is less than, means that less than, we should add another one to give equals to 0. When it is greater than, then we should minus with slack variable, then it is equals to 0. And here is already equals to 0, then we just can write it again equals to 0. Okay, is that clear? Any question? Okay. So now, from this constraint, because we do some modification on this constraint, we are going to identify which constraints are active or passive constraint. Okay, we adding slack or surplus, then we are going to check whether which constraint are active and or passive constraint. Okay, so now, okay, assume, all right. So how can we identify this active or passive constraint? Let's assume we have x and plus 1 here greater or equals to 0. What is x and plus 1? Is the slack or surplus variable. Okay. So now when you are assumed that x and plus 1 greater or equals to 0, there are two conditions that we need to consider. Okay, whether x equals to 0 or x greater than 0. Okay, so in x and plus 1 equals to 0 here, okay, the optimum point is located on the boundary gx equals to 0. Okay, so if for this case x and plus 1 equals to 0, the optimum point is located okay when x n equals to 0, when x n plus 1 equals to 0, okay, the optimum point is located on gx equals to 0, then we say that the constraint is active constraint. Right? Okay, and then the second one, the second case, where xn plus 1 greater than 0. So for this case, the optimum point is not located hence it is passive constraint. Okay, so now how can you identify which one are active or passive? Let's say we have xn plus 1 greater or equals to 0. Then when x equals to 0, The optimum is located on the boundary. When the optimum point is located on the boundary, then we say that this is active constraint. Okay, but when the optimum point is not located on the boundary, hence it is a passive constraint. Okay, so there are relation between passive constraint and also Lagrange multiplier. Okay, so if the Lagrange multiplier will minimize the function with this inequality constraint, okay, where after we convert, we have this constraint, then X is a vector which is a slack variable and also together with surplus variable. Okay, so how can you understand this? All right, so up to this point, clear or not for this part? We have inequality, okay, where you know that there are constraints which is inequality signs there, okay, and then you convert to equality constraint by adding slack or surplus. Hence, we have this general form of constraint optimization, which is equality constraint right now, okay, and we want to identify which constraint is active or passive. So up to this point, any question? Okay, all clear? So now how can we relate this form of general inequality to equality constraint here? How can we relate this to Lagrange multiplier? Okay, so of course, in order to find the optimum point, it is always use this sufficient or necessary condition here. Okay, where for this case, can you see it or is it too small? Okay. Right, so we are going to have the necessary condition of del f del xn plus 1 equals to 0. So by Lagrange, if we relate all the variables here, we are going to have f, x, xs, and lambda, where xs here, what is xs here, is a vector, okay, for both slack and surplus variable. Okay, so this f can be written as fx plus summation of lambda 1 gix plus xn plus 1 okay, plus summation of minus xn plus 1 plus summation of I equals to so as you can see, it is quite identical with the general form of Lagrange multiplier here, right? This one. This Lagrange multiplier, we just add the objective function with the constraint multiplied with lambda. But for now, this Lagrange multiplier here is the summation of function, the objective function, the constraint with slack variable, the constraint with surplus variable, and also the constraint, the equality constraint. Okay, so that is the difference between the equality and inequality. Of course, they are quite identical once you convert to equality, but we have to consider all slack and plus variable that we use. So that's why the Lagrange multiplier function here is uh, quite long compared to the previous function. All right, clear now? Okay, try to understand this first. If you have question, you can ask. Okay, no question? All right, after this, what? Once you have your Lagrange multiplier function, then what? According to the previous example. Anyone? Yes, we have to differentiate. Right. The necessary condition df dx equals to 0. Okay, but now let's check. So when I equals to 1 up until u, as you can see here, del f del x and plus 1 equals to lambda I. So do we differentiate this? Right, we are going to have lambda I. Okay, equals to 0. And when I equals to here u plus 1 until v, then we have here del f del x and plus 1 equals to negative lambda I equals to 0. Okay, so what we can conclude here for this passive constraint, okay, the Lagrange multiplier take 0 as take 0 in the optimum, point, because we have here 0, 0. There is no solution for x n plus 1 here. So for this one is for passive case, right? Okay, for passive case here, we are expanding the Lagrange multiplier up until this. But when we differentiate, we have lambda I both 0. So we can say that for this passive constraint, the Lagrange multiplier take 0 in the optimal point. So in another word, if the constraint, the passive constraint in the optimum point, hence we can just neglect the constraint in order to find the optimum point. So in another word, we can just neglect the passive constraint, because once you identify here as a passive constraint, then we can expand up until this Lagrange multiplier. But once you proceed with derivative of f with respect to xn plus 1 here, you are going to have lambda both equals to 0. So we just can assume that this passive constraint take 0 in the optimum point. Okay, so that's why, hence, after this, we are going to discuss about the condition of Kant-Tucker to solve this kind of problem. Okay, is that clear? Okay. So now, before this, we have 0 as our optimum point after we solve this Lagrange, right? So now we have this Kant-Tucker condition to overcome the problem. So we have 4 conditions of this theory of Kant-Tucker, okay, where we are going to have our optimum point at x value. Right? So these are the conditions. Now, let's see how can we apply this condition. How we can understand this condition. Okay. So theoretically, let's discuss it theoretically first before we proceed with the example. Okay, we have this problem. We want to minimize z, an objective function, okay, of fx here, such that the constraint is less or equals to 0. So now our Lagrange multiplier will be given by, okay, anyone want to try? According to this, what is the Lagrange multiplier of this problem? We have less or equal, so we should have what? Surplus or slack? So what is your Lagrange multiplier form? You should have what? So f x s and lambda equals to, if it is less than, we should add or minus. If it is less than, what should we have? We should plus with what? Yes, slack, right? We should plus with slack of x and plus 1. Slack and surplus both are x and plus 1, but you need to identify whether you have to add the x plus 1 or minus with x plus 1. You have to add with slack or you have to minus with surplus. So for this case, it is less than, then we just have what? Here we should have another function of x, and or can write it as surplus equals to 0. Sorry. Then we have here fx plus lambda gx plus with x. This is our slack. Okay. Clear? Any question? Okay, guys. Why so silent? Are you understand? From 1 to 10, where are you now for this topic? Okay. Now let's consider. Let's consider this problem. Okay, so assume that this is a minimum case, minimizing case. Okay, if the side, the right hand side of gx greater than 0, okay, Okay, here is your constraint, right? If the right hand side of gx less than 0 increase, so increase from 0, so f cannot be increased anymore because we have up until less or equals to 0. So it is less or equals to 0, then we increase to 0. Okay, then f cannot be increased anymore because the constraint is less or equals to 0. Okay, then if this one is for case minimizing case, minimum case. Okay, and if for maximum case, right, if g increase, f cannot be decreased such that lambda cannot be greater than 0. So it is less or equals to 0. So that's why from this, we can obtain lambda equals to derivative of f and derivative g here. So the negative del f del g. So solving this will give you lambda equals to negative del f over del g. So for minimum case, if the right hand side of this gx increase to 0, then f cannot be increased anymore because the limitation is only up to less or equals to 0, up only to 0. Understand or not? So let's say this is your function f, right? And your g is less than or equals to 0 here. So if it is increased to 0, then your f cannot be increased anymore because it is limited to that constraint. Is that clear or not? Understand or not? Okay, so this one is less than. Okay, for minimum case. Then if gx equals to 0, then lambda cannot be limited anymore. Okay, so this limitation of lambda is a part of the Kan-Tucker condition that we need to fulfill. So that's why there are a lot of Kan-Tucker condition here which involve the value of lambda. As you can see, all of these conditions involve with lambda here. All right. So how can we use it? Let's try to understand this according to example. Eh? Okay, so any questions? All right. So here we want to minimize. Here we want to minimize the objective function. All right. And in order for f cannot be increased anymore, for minimum case, that gx must be less or equals to 0. So we need to convert this to less or equals to 0. So for this one will become what? Minus x1, right? Less than 0. This one also minus x2 less than 0. And this one minus x1 minus x2 less or equals to minus 4. So substituting into the Lagrange, and lambda, okay. So we have fx, 3x1 squared plus 4x1 x2 plus 5x2 squared. And then this is less than, so we should plus with plus here. Okay, so we have lambda 1 because we have 3 constraints. So we are going to have up until lambda 3. So lambda 1 S1 minus x1 plus lambda 2, s2 minus x2 plus lambda 3, s3 minus x1 minus x2 plus with 4. Okay, clear now up to this point. Okay, so you have to find what is your del f, del x1, del f, del x2. Okay, find it. What is del f, del x1 and del f, del x2 here? Anyone? Six x1 plus 4x2 minus lambda 1 minus lambda 3. Right. And then another one is, what is another one? For x1 plus 10x2 minus x2 minus lambda 2 minus lambda 3 equals to 0. Okay, so up until now, what we have done is applying the Cantucker condition, convert the constraint to less than equals to 0 and apply to this Lagrange multiplier and apply the necessary condition of del f and del xi. Okay, so up until now, any question? No question. Okay, good. Okay, now we want to apply the contactile transition. Okay, so first we have here the constraint x1 less or equals to 0. Del f del x. Sekejap saya cek sekejap.